Hi, welcome to Algebra 2 Common Core. Today we're going to finish up Unit 10 by talking about the remainder theorem. We've spent some time throughout this unit talking about when we get remainders when we divide polynomials. So we're going to focus on that first of all today. The first question says, is -4 a root of the polynomial function y equals 2x to the fourth plus 8x cubed plus 2x plus 8? Now, this is the same as asking the question, is x plus 4 a factor of the polynomial? So to figure out whether -4 is a root and subsequently if x plus 4 is a factor, so far what we have done is done division. Now we can either do division using our long division or our box division. I'm going to switch back and forth between both in this lesson so that we get practice on both of them. So let's start by doing a long division. So I've got 2x to the fourth plus 8x cubed plus 2x plus 8. And I want to divide by x plus 4. Now, I know that it's going to be a factor if the remainder turns out to be 0. If the remainder is any other number, then x plus 4 is not a factor. So x goes into 2x to the fourth, 2x cubed times, I didn't leave enough room there. So that gives me 2x to the fourth plus 2x cubed times 4, which is 8x to the third. Now, with this process, I'm going to go ahead and subtract. And that gives me nothing left there, so I'm going to bring down my next term, which is 2x, and I may as well bring the plus 8 down as well. 2x divided by x gives me a plus 2, so 2 times x is 2x, 2 times 4 is plus 8, and when I subtract that, I do see that the remainder turns out to be 0. So, since the remainder is 0, that tells us that x plus 4 is a factor of that polynomial. And then that also means that x equals -4 must be a root, because if x plus 4 is the factor, when I set that equal to 0, it solves as x equals -4. Also remember that once I found this factor of x plus 4, this polynomial could be rewritten as x plus 4 times the quotient, which was 2x to the third plus 2. If I wanted to find the roots, I could set that equal to 0, and solving, I see that yes, x equals -4 is one of the roots. Now let's go ahead and try another example of this. Is 2 a root of this polynomial function? So again, this is the same as asking the question, is x minus 2 a factor of the polynomial? So to find out if it's a factor, I'm going to do a division and see if the remainder turns out to be 0. Now, just to practice our other form of division, I'm going to set up a tabular method. So I'm going to say I am taking my polynomial and I'm dividing by x minus 2. So when I do that, I'm going to start with 3x to the third. So 3x to the third divided by x gives me a 3x squared. Multiply that by -2, and that's a -6x squared. Now I know that my diagonal here has to add up to -6x squared, which it does, so that tells me that I've got a 0x squared up here. So on top, 0x times x gives me 0x squared, and this is going to give me a 0x in that spot. Now this diagonal has to add up to 2x. So that tells me that I must have a 2x right here. Go ahead and figure out what I have to multiply x by, and that's going to be 2. 2 times x is 2x. 2 times -2 is -4. Now here's an instance where I'm going to say that this last number here does not match this last number here. So I have to add on an extra. I have to add on a 5 in order to get that diagonal to be equal to this. Now when I had to add on that 5, That 5 then turns out to be the remainder in the division. So if that's the remainder, that then tells me that x minus 2 is not a factor of the polynomial. So that also means that x equals 2 is not a root. So I've demonstrated one way of determining whether a number is a root or a binomial is a factor of a polynomial. We can do division and see if our remainder turns out to be 0. If the remainder is anything but 0, then I know that I do not have a factor and I don't have a root of the original polynomial. So let's move on to our exploration, where we're going to start to investigate another method for finding out if I have a factor or if I have a root of a polynomial. So on the left side, you'll see that I'm doing a division. For the first one, let's go ahead and do our box division again. So I'm going to say, okay, let's be able to tell if x minus 2 is a factor of x squared minus 8x plus 18. So do the division using the box. So I know that I have to multiply by x. X times x is x squared. X times negative 2 is negative 2x. But I know that I need a negative 8x here. So when I make my next column, the diagonal has to equal negative 8x. So that tells me let's fill in a negative 6x. Do the quotient by saying what do I need to multiply x by to get negative 6x, and that'll be a negative 6. Negative 6 times x is negative 6x. Negative 6 times negative 2 is positive 12. Now again, when I get to that number and I see that that number does not match this number, I'm going to have to fill in the next column, what do I have to add to 12 to get 18? I see that that is 6. Now, that 6, I can't keep going with the division because there's nothing that I can multiply x by to get 6. So that last number that I had to fill in here is my remainder. So I see that in the division, this division is going to give me x minus 6 plus the remainder of 6 over the divisor x minus 2. So x minus 2 is not a factor. Now, going off to the right side, we're going to investigate something completely different, supposedly. What are we going to do? We're going to take that number 2. Where's the 2 coming from? If I take my factor of x minus 2 and I set it equal to 0, that gives me the root x equals 2. So that's why I'm putting 2 in right here. I want to find the function value at 2. So that means let's substitute 2 in for x. So I'm going to say 2 squared minus 8 times 2 plus 18. 2 squared, of course, is 4 minus 16 plus 18. Adding all of that together, I get that p of 2 is equal to 6. Well, that looks very familiar. This number happens to be exactly the same as my remainder number. I wonder if that's a coincidence, or will that always happen? Let's try one more example here. So I want to do the division. This time let's do a long division again, just for practice on both of them. 2x squared plus 11x plus 11. I'm going to divide by x plus 3. So 2x squared plus 6x. Subtract this line, and I'm getting 5x plus 11. 5x divided by x gives me a 5. 5 times x is 5x. 5 times 3 is plus 15. So let's go ahead and subtract, and I see that this time my remainder is negative 4. So off to the right here, let's do the same thing. Let's take our factor, x plus 3, and set it equal to 0, and get the root x equals negative 3. Put that negative 3 in for x, so substituting, I get p of negative 3 is equal to 2 times negative 3 squared plus 11 times negative 3 plus 11. So, doing the calculation, 2 times 9 minus 33 plus 11, 18 minus 33 is, of course, negative 15 plus 11 gives me a final answer of negative 4. So p of negative 3 also gave me negative 4. So I'm seeing a correspondence here between the remainder when I do division of the factor and the function value when I substitute the root into the very same polynomial. Now, what we have just seen evidence of in this exploration is called the remainder theorem. We haven't done a proof, we've just tried out a few examples to see if it works a few times. The remainder theorem says that when I take a polynomial and I divide it by a linear factor, it can be in the form of x minus a or x plus a, then when I substitute the root into the polynomial function, the remainder stays exactly the same. So what this tells us is that we really have two ways to decide what a remainder is. And when we get that a remainder is equal to 0, in two ways we can decide whether I've got a factor or a root of a polynomial. So I've got options here. So the two ways that we have been using to determine if x minus a is a factor of a polynomial, the first way is going to be to divide the polynomial by x minus a. If when we do that division, and remember that our division can either be done using the box method or using long division, if the remainder after the division turns out to be 0, then that tells us that x minus a is a factor. We can also use this new theorem, the remainder theorem. So if we find the function value p of a, then if the function value of the root is 0, that tells us that the remainder would be 0 if I did a division, and that x minus a is a factor. A lot of times we're going to want to use this remainder theorem because it's a quick and easy way of deciding if I do have a factor, and subsequently if the number is a root of the polynomial. So let's try a few examples of using the remainder theorem. If we want to know if x minus 3 is a factor of p of x, then what we're going to do is test it by saying, using the remainder theorem, what's p of 3? Now when we're finding p of 3, we'll substitute 3 in for x, so we're getting 3 squared times minus 11 times 3 plus 24. Doing that calculation, 9 minus 33 plus 24 does turn out to be 0. So since I have an answer of 0 for my remainder, that tells me that yes, x minus 3 must have been a factor. That also means that 3 is a root of this polynomial. 3 would be the place where the graph crosses the x-axis. Let's try the next one. Is x plus 5 a factor of p of x? So in order to test this, we have to remember, take that factor, x plus 5, set it equal to 0, solve for the possible root, in this case negative 5. So I want to find p of negative 5. That's going to be 2 times negative 5 squared plus 9 times negative 5 minus 2. When I do that arithmetic, I end up with an answer of 3, so p of negative 5 is equal to 3. That's my remainder, so since the remainder is not 0, That tells me that x plus 5 is not a factor of that polynomial. In part C, it says, is x equals -1 a root? So for this one, we're already given the root, so we just want to find p of -1. So we're going to say -1 cubed minus 7 times -1 squared minus 11 times -1 minus 3. And again, you can definitely use your calculator for this. You can either substitute the -1 in and do the calculation like I've done. You can also store -1 in your calculator for x and then type the polynomial just on your home screen, and it'll give you the function value of the polynomial. So I use that method quite a bit. For this one, I end up with p of -1 is also equal to 0. So that tells me that yes, I do have a root. -1 is a root, and that also tells me that x plus 1 would have been a factor of the polynomial. I'm trying to differentiate between the two questions that could be asked. Take a minute to try the last one. We want to know, is x equals 5 a root of p of x? So go ahead and try that one. I'll do my substitution and we'll compare answers afterwards. So I found the function value p of 5. Make sure that even if you're doing this in your calculator, you do need to show the work of substituting the 5 into the function to show that you're using the remainder theorem to solve this problem. So when I substituted 5 in and then put that on my calculator, I got a -5 for my answer. Since that answer is not 0, that tells me that x equals 5 is not a root. And if x equals 5 is not a root, that means that x minus 5 is not a factor. The remainder theorem can also help us solve other types of problems. So if I know, let's see here, in example number 4, it says, for what value of k will x minus 4 be a factor? So if I want it to be a factor, first of all, I'm going to solve for the root. So I'm going to say x minus 4 equals 0. So the root that I'm going to use is x equals 4. So when I'm using the factor theorem, I have to have the root number to be able to put in. So I'm going to find the function value p of 4 for this function. So I'm going to say 4 squared plus k times 4 minus 52. Now, if it says that I do want this to be a factor, that means that the function value by the remainder theorem has to turn out to be 0. So let's just do the calculation here. So I've got 16 plus 4k minus 52 is equal to 0. So 4k minus 36 must equal 0. 4k must equal 36. So k must be 9. Now let's go back and do a little check here. I'm going to take my polynomial and substitute 9 in for k. So I've got x squared plus 9x minus 52. So the question is, can I rewrite this as the product of x minus 4 and some other binomial so that they multiply to give me x squared plus 9x minus 52? Well, this is one of our easy factoring. So I want to add to get 9 and multiply to get negative 52. I already know that one of the factors is negative 4, so that tells me that the other factor must be x plus 13. Now if I go ahead and multiply that, I do get this trinomial as my answer. So that tells me that if I can write this in factored form, that x minus 4 is a factor when my k value is equal to 9. And in fact, that's the only time I'm going to get an answer where I have no remainder, when k is equal to 9. Now another very useful thing that I can use the idea of factoring and finding roots is trying to break down higher order polynomials. So for example, if I've got x cubed minus 12x squared plus 12x plus 80, right now we have no way of knowing how to factor that. But if we're given one piece of information, that one piece of information can help us find the other factors. So if x equals 4 is 1, 0, then what that tells me is that x minus 4 is going to be a factor of this polynomial. Well, if I know that it's a factor, that means that when I divide the polynomial by x minus 4, I'm going to get another polynomial factor to multiply by x minus 4. So again, you can choose whether you want to use long division or the box. So I think I might do another long division here. X cubed minus 12x squared plus 12x plus 80. When I divide this by x minus 4, I'm getting x squared. So that's going to be an x cubed minus a 4x squared. Subtract, and make sure you subtract a negative, so that's a negative 8x squared plus 12x. Divide by x again, so negative 8x. Negative 8x times x is negative 8x squared. Negative 8x times negative 4 is positive 32x. Subtract, and that's giving me negative 20x. Bring down the plus 80. Divide again, and that's going to give me a negative 20. So I now have negative 20x plus 80, and I saw, yes, because x equals 4 was a 0, I knew I was going to end up with a remainder of 0. But the additional information that I was able to gather is the other polynomial, the quotient. So that tells me that if I take my polynomial, x cubed minus 12x squared plus 12x plus 80, and I know that one factor is x minus 4, then I know that the other factor is going to be that quotient, x squared minus 8x minus 20. Now I can additionally see in this case, I end up with a trinomial that can be factored. So this is going to be x minus 10 times x plus 2. If my trinomial was not factorable, I would have to use one of my other methods, like quadratic formula or completing the square to find the other roots. Now, since I want to find the roots or the zeros, I set this equal to 0, and I go ahead and I make my t-bar. So I'm getting x equals 4. Well, that's good because that's what I was told from the beginning. X equals 10, and x equals negative 2. Now, a quick and easy way to check these roots would be to find the function value, the polynomial value at 4, the polynomial value at 10, and the polynomial value at negative 2. If all of these are indeed factors or roots, then these answers for the polynomial should be 0. Now, once again, I could store each value in my calculator for x, and then when I type in this polynomial and press enter, I should get 0, showing that all of these have a remainder of 0 when they are divided. So it's a nice, easy way to check. Now I'd like you to try the you try it. So we want to know this time if x equals negative 1 is a 0 of this polynomial. So that's another way of asking, is x plus 1 a factor? So I did the division, and when I did the division, I did it by long division, so you can follow my steps and see if you got the same answer. I did get a remainder of 0. But here was the trinomial that was the other factor. So that tells me that I can write this polynomial as the product of x plus 1 times x squared plus 8x plus 14. So since I had a 0 at x equals negative 1, that's a nice easy one to find. But the other one, unfortunately, is not factorable this time. So that told me that I had to use the quadratic formula to find the other zeros. Now, let's take a look at how many zeros I've got there. Here's 1, and then by using the quadratic formula and simplifying it, I'm getting 2 more zeros, 4 plus radical 2 and 4 minus radical 2. I should have had 3 zeros because I had an x to the third in my polynomial, so it makes sense that I got these 3 roots, or zeros. You'll notice that all 3 of them are real. This one is real and rational. These 2 are real and irrational. And they, of course, are conjugates of each other. Thanks for working on factors and remainders tonight. We'll do some more work in class, and have a great night. See you next time.